We're going to look at only 3 reactions that alcohols will undergo.
We've seen that they can be formed by the hydration of alkenes. We saw that in the previous chapter. But they will also undergo the reversal of that reaction, and water can be removed to form the alkenes. Alcohols will undergo condensation, which is the removal of water. Can get confusing with dehydration. We don't call it dehydration, but we call it condensation, when 2 molecules are joined together by the removal of water. We'll look at that a little bit. That forms an ether. And then alcohols can be oxidized. When we were looking at oxidation and reduction, we saw that you can have oxidation by the reduction in the number of hydrogens on a carbon, or we could have reduction by the addition of hydrogen to carbons. Well, here we're going to look at just that thing. We're going to see that alcohols can be oxidized to aldehydes or ketones by removing hydrogens. The first reaction that we're going to look at is the dehydration reaction. If you look at this alcohol below, you can see that you can remove a hydrogen from one carbon and a hydroxyl group from another. The 2 of those can be joined together to make water. This forms an alkene. We've looked at the reverse of this reaction already, where we took water and an alkene and added them together, and we called it hydration, and we made an alcohol. Now we're showing you the reverse of that reaction. Again, sulfuric acid is needed for this reaction to occur. It's a catalyst. Here are some examples. We can take ethanol in the top, treat it with sulfuric acid, and remove water to make ethylene. In the bottom example, we can take cyclohexanol, remove water, and make cyclohexene. To figure out how to do this, all you do is you identify the carbon that has a hydroxyl group on it. You remove the hydroxyl group from that carbon, and then from an adjacent carbon, you're going to remove a hydrogen so that a double bond will be between those 2 carbons. Here is a molecule that I'd like you to try to do that on. Notice there's the hydroxyl group on a carbon. So you're going to remove water from this molecule to form a carbon-carbon double bond. Go ahead and try to do that and see if you can come up with the right answer. Okay, what I did here was I went and I took the oxygen and the hydrogen, the hydroxyl group, off the carbon that had it on it, and then I moved next door and I got a hydrogen off the carbon that is next door. That removes water from that molecule, and so a double bond forms between those 2 carbons. I chose the carbon that was right there with the hydrogens drawn attached to it rather than one of the carbons that is on the end of the chain for a reason that we're not going to go into in this course. We find that internal double bonds are made much more frequently than ones that are on the end of a chain. So that's why I did that. But that's beyond this course. We're not really going to worry about where the double bond forms as long as you can form the double bond. Condensation is the joining of 2 molecules by the removal of water. So if I look at this example here, I'm forming an ether by joining 2 alcohols together by removing the water. So the alcohols I'm writing in a generic form by writing ROH, where R is any carbon chain, and then there's a hydroxyl group, and then I've flipped around the other alcohol so it's facing the other alcohol so you can see this a little bit better. Notice I'm taking a hydrogen from one alcohol and a hydrogen and an oxygen from the other alcohol, and then the 2 are being joined together to make an ether. This is an equilibrium reaction, which you can see with the double arrows, and we can force this reaction to completion by the removal of water. We can actually force it toward the alcohols by adding lots of water, or we can force it toward the ether by removing lots of water. So this is an example of how we can control reactions by using the principles in equilibrium. Here is an example of two ethanol molecules being joined by condensation to form diethyl ether. You can see I'm taking away one hydrogen from one of the alcohols and an oxygen and a hydrogen from the other alcohol. This causes this to form diethyl ether. So now look at these two problems. You've got two different types of alcohols. Decide which ether would form, or what ether would form from each of these reactions. If you remove water to form the ether, what would be the product of condensation? If you have condensation of two methanols, as we're showing here, water would be removed and you would have a methyl on either side of an oxygen, and two methanols form dimethyl ether. If I look at cyclopentanol, two cyclopentanols would be joined together so that there's a cyclopentyl on either side of the oxygen, and we call it dicyclopentyl ether. Alcohols can be oxidized also. If you remember oxidation when we covered it earlier in the semester, we saw that oxidation was an increase in the number of carbon-oxygen bonds or a decrease in the number of hydrogens bound to carbon. So let's look at oxidation here with the alcohol that I've shown below, a representative alcohol. If I take this alcohol, you can see I can remove two hydrogens from the alcohol, one from the oxygen and then one from the carbon to which the hydroxyl group is attached to. That forms another oxygen bond to carbon, and this entire step is classified as oxidation because not only is the number of carbon-hydrogen bonds decreased, but the number of carbon-oxygen bonds increased. You can see that we give as a general way of indicating oxidation occurs or oxidizing conditions is to write a bracket and then an oxygen and then a bracket. That's our general symbol for oxidation. Reduction is the opposite of oxidation, and if I take a carbonyl and reduce it, the symbol for reduction is a hydrogen in brackets, like an oxygen is a symbol in brackets is a symbol for oxidation. If I reduce a carbonyl, as shown here, what happens is I add back the hydrogen to the carbon and the hydrogen to the oxygen and break that carbon-oxygen double bond down to a single bond. So basically the two hydrogens are added across the carbon-oxygen bond. So this is the reduction. Oxidation would be going backwards on this reaction. Reduction is going forwards on this reaction. When we first looked at alcohols, we saw that there were three different types of alcohols: primary, secondary, and tertiary. When we oxidize each of these different types of alcohols, we get different products. So we're going to look at primary, secondary, and tertiary alcohol oxidation. The first one shown here is primary alcohol. Down here we're showing ethanol, which is a primary alcohol. You can see the alcohol is at the end of the chain, and the carbon on which the hydroxyl is attached, there's only one other carbon on it. When this is oxidized, what happens? Well, a hydrogen is removed from the oxygen, and then a hydrogen is removed from the carbon to which the hydroxyl group is attached. So that gives us a carbon-oxygen bond there. That's a carbon-oxygen double bond on the end of a chain, which makes it an aldehyde. Aldehydes are very susceptible to oxidation, and they can be further oxidized two carboxylic acids. Basically what happens when an aldehyde is oxidized, and oxygen is essentially inserted between the carbon in the carbonyl and the hydrogen to which the hydrogen that is attached to the carbonyl, and that gives us the carboxylic acid there on the right. When secondary alcohols are oxidized, a different product occurs. You can see the secondary alcohol has a hydroxyl group in the middle of a chain. That hydroxyl group is attached to a carbon with two carbons attached to it in 2-propanol. We remove those two hydrogens, the hydrogen that's on the oxygen and the hydrogen that's on the carbon that's attached to the hydroxyl group, and then a carbon-oxygen bond forms, and we get a ketone, a carbonyl in the middle of the chain. Here we're seeing 2-propanol being oxidized to acetone. And remember, reduction is the opposite of oxidation, so when we go from 2-propanol to acetone, that's oxidation, but acetone can be reduced to 2-propanol. Tertiary alcohols have no hydrogen on the carbon that has the hydroxyl group on it. That means you cannot form a carbon-carbon double bond. Tertiary alcohols cannot be oxidized. So when you submit a tertiary alcohol to oxidizing conditions, no reaction occurs. Let's look at some examples. The first compound on top is 3-pentanol. 3-pentanol is a secondary carbon. You can see there is a hydrogen on the carbon that the hydroxyl group is attached to. So when oxidation occurs, the hydrogen on the oxygen and that hydrogen on the carbon can be removed. This forms a carbon-oxygen double bond in the middle of a chain. If I look at the product, you can identify that it is a ketone with 5 carbons, and we'll learn how to name that later. If I look at the next compound, you can see that the carbon on which the hydroxyl group is attached has 3 carbon chains on it. This compound is actually called 3-ethyl 3-pentanol. If you draw it out, you might be able to figure that out. Now, when this is oxidized, since there is no hydrogen on the carbon to which the hydroxyl group is attached, no reaction can occur. In these examples, the top alcohol is 1-butanol. 1-butanol is a primary alcohol. The alcohol group is on the end of the chain. The hydroxyl group is on the end of the chain. What would be the first product formed when you oxidize this? Well, oxidation is going to remove a hydrogen from the hydroxyl group and from the carbon that the hydroxyl group is attached to. That will form a carbonyl there. So the first product is the aldehyde shown there, the 4-carbon aldehyde. That product would be oxidized and would then form a carboxylic acid. So the aldehyde would then be converted to a carboxylic acid. Okay, now pause the lecture and try these 2 problems. What would be the product of oxidation for these 2 compounds? Remember to remove a hydrogen from the carbon that the oxygen is attached to, and remove a hydrogen from the oxygen that is attached. It is a hydrogen from the oxygen also. It will form a double bond between the carbon and oxygen then. For the first one, if you look at it, you can see that this is a tertiary alcohol. The carbon that the oxygen is attached to has 3 carbons attached to it, and so there is no hydrogen on that carbon. Because there is no hydrogen on that carbon, no oxidation can occur. So there is no reaction with this one. With the next one, it is a secondary alcohol, so there's only 2 carbons attached to the carbon that has the oxygen on it, so you can remove a hydrogen there. There is a hydrogen on that carbon, so you can take that hydrogen off and the hydrogen that is on the oxygen off, and it forms a double bond so that a ketone is formed. So if you're trying to remember how this works, if it's a tertiary alcohol, there is no reaction. If it's a secondary alcohol, oxidation causes the ketone to be formed. Go ahead and pause the lecture and try to do the oxidation of this compound, the first and the second product oxidation. For the first step of oxidation of this alcohol, you would form an aldehyde. This is a primary alcohol, and primary alcohols actually have 2 steps of oxidation. In the first one, you take the hydrogen that is on the oxygen off and the hydrogen that is on the carbon attached to the oxygen off and form a double bond between that carbon and oxygen. So you can see that an aldehyde is formed as the product of this reaction. The aldehyde then can undergo oxidation again. So the second step is, or the second oxidation product is, that you would have the aldehyde oxidized once more. To have the aldehyde oxidized once more, what happens is an oxygen is inserted between the carbon and the hydrogen that has the double bond oxygen on it. So what happens is you get a carboxylic acid. So now there's 2 oxygens on that carbon, and it's a carboxylic acid.